Hi everyone, thanks for joining my talk. Apologies for not being able to be there in person. My name is Kubakashik. I'm from the University of Edinburgh. Today I'll be presenting our work on performance-aware convolutional neural network channel pruning for embedded GPUs. So I'll give a brief overview of the talk. First, I'll give some background on convolutional neural networks and channel pruning. Then I'll look into detail on channel pruning on NVIDIA GPUs, channel pruning on ARM GPUs, and then finally I'll share some library insights that we had with the GPU simulator. So what are convolutional neural networks? So CNNs are very similar to ordinary neural networks. They're made up of neurons that have learnable weights and biases, and each neuron receives some inputs, performs a dot product, and optionally follows it with a nonlinearity. So what changes? CNNs make the explicit assumption that the inputs are images, which allows us to encode certain properties into the architecture, and these then make the forward function more efficient to implement and vastly reduce the amount of parameters in the network. So if you imagine that this was a fully connected neural network, you'd have connections between each each pixel in the input image throughout the entire network, all the way through to classification. In CNNs, we still have some fully connected layers, but the vast majority is spent at these much smaller convolutional layers that only look at subsets of the subcomponents of this image, really, and only make connections between these small parts. So that, again, lets us vastly reduce the amount of parameters in this network. So CNNs are becoming common presence in many applications and services due to their superior recognition accuracy. In computer vision, they're used in image classification, segmentation, detecting objects in images, but they can also be used in other sort of areas. For example, in speech recognition, you can transform audio into these spectrograms, which are basically images that can be fed into a convolutional neural network. Or in natural language processing, we use something called word embeddings, where words or phrases from the vocabulary are mapped to vectors of real numbers, and then a 1D filter is convolved over the dictionary. So why are we focusing on convolutional layers? It's because they take up the bulk of the computation time of most CNNs. So if you look here, convolutional layers take up roughly 80 to 90% of the time in a convolutional neural network. AlexNet has a few more fully connected layers, but it's an older network, so if we focus on the newer ones, then the majority of the time is spent in these convolutional layers. Some other layers that we might find are Rayleigh and batch normalization, but again, they take up a very small percentage of the actual inference time. So let me show you how a convolutional layer works. Let's assume we want to classify this image here. So first we split it up into 3 separate channels. In this case, RGB, red, green, blue. And once we've got that ready, we take a series of filters and we convolve them over the input image. And we do this by overlapping the filter on the image and sliding the filter 1 pixel to the right and so on until the whole channel is covered. This basically reaffirms the fact that there are very few connections between successive layers of a CNN compared to a fully connected neural network. And at each step here, we perform the dot product between the filter and the segment of the image that is overlapping. And the result is a 2D activation map for each filter to channel application. So again, if we have M filters, the result here is M channels in the output layer. This method here is called direct convolution. In practice, it's quite expensive to be sort of sliding this filter over the entire image and computing all these things one by one. So another method that is used is called im2call, where we basically take these 3x3 image squares from our input image, and we turn them into column vectors. If you do this for each image square and then compose it into a matrix, the result is a matrix with columns equivalent to a 3x3 image square. And similarly, the filters can be transformed into row vectors, and you end up with this matrix where each row is essentially one of these filters. And once you have this type of representation, you can leverage highly optimized gem libraries to perform a matrix multiplication between these two. And the result, again, is exactly the same as it would have been with gem. But this approach requires much more memory. So if we're replicating each of these squares as a column, then there's a lot of overlap. For example, if you assume that you've got this sort of if we've got padding of 1 pixel on each side, so we've got just zeros along the edge of the image here, and we've got a stride of 1, which basically means that we're moving uh, our filter 1 pixel by 1 pixel over the image. What this results in the end is 25 times 9, so 225 pixels needed to store this 5 by 5 image, whereas for a direct convolution, we just have that those original 25 pixels that we needed to store. So in total, that's 9 times more memory that you're using in this case, in this sort of extreme case. In practice, I mean, when you have a desktop GPU, you have loads of memory to accommodate the data and the network structure entirely. You've got 12 gigabytes, for example, in NVIDIA Titan X. But that's not the case in a lot of mobile and embedded GPUs or smaller devices. So ARM predicts that by 2035, we'll have 1 trillion new IoT devices, and they'll be of all shapes and sizes. So with the growing number of applications that use CNNs and edge devices, we need to consider how to optimize CNNs for these types of small devices. So in this graph here, we're showing the log scale for the amount of memory that's required for MTCall and direct convolution for these different neural networks. And we can say, well, we know these small devices, sometimes they only have kilobytes of memory, but MTCall often surpasses, I mean, it exceeds 100 megabytes in many of these cases. So it's not a practical solution for these small devices. And even if you consider some of the embedded GPUs that we have, for example, the IISWC'19 development board, which has Mali G71, 3 gigabytes of memory. There's 3 gigabytes of memory there, but that memory is shared between the CPU and GPU. You have a whole operating system that needs to run alongside that. You've got other applications running. So in the end, you're really not working with a lot of memory, even on these embedded GPUs, compared to what you'd get on a big NVIDIA GPU. So what can we do about this? There are a number of compression techniques which aim to reduce the memory and computation requirements for CNNs. Some of these include weight pruning, channel pruning, hashing, quantization. In this work, we focus on channel pruning because that allows us to keep this dense matrix multiplication that we've been working with. So let's assume we want to prune these 3 output channels. So 1, 2, 3. What would happen is that we'd remove the 3 corresponding filters, so that computation would never happen in the first place, right? So here's the input layer. We remove 3 of the filters that correspond to these 3 output layers. And what we end up with is this convolutional neural network with a reduced number of channels. This layer has a reduced number of channels. And basically, what we have to do once we prune that, we have to refine the weights again with the training. We have to reindex the channels so that we can use the dense operations, and that will generally happen on a much larger desktop GPU, and we'll bring that trained network back onto an edge device to perform the inference. So some brief motivation for the work that we're doing. Basically with channel pruning, since you're reducing the number of channels, you're reducing the amount of work that you need to do. What you'd expect is speed up every time you prune a channel. But what we've observed is that that's not always the case. On the left-hand side, we have the number of channels that we've pruned, and in the squares, we have the maximum slowdown that we've experienced with those number of channels pruned. So basically you can see here that there are cases in this space, for example, for resonant layer 0. There's some case between 7 and 15 channels that we pruned where we experienced a slowdown of 1.6x. So that's obviously significant, especially because you're not expecting any slowdown at all when you're pruning channels. So we ran a bunch of experiments based on this observation. We used a couple different networks, ResNet50, VGG'19, AlexNet, and they all have different numbers of layers and filter size and different filter sizes. We evaluated the following libraries on the following platforms: so ARM Compute Library on the HiKey'970 and the Odroid board, cuDNN on the Jetson TX2 and the Jetson Nano, and TVM on the HiKey'970. So looking at the performance with cuDNN, we see what we want to see. Basically, that as we reduce the number of channels here, the inference time drops But what we see here is that there's a non-linearity between the number of channels and the amount of inference time. So that's something that you definitely want to take into account when channel pruning. It's basically saying how much speed up can you actually get by pruning these channels. And if you prune 5 channels here versus 5 channels here, you'll definitely get a different speed up. So overall, with cuDNN, we didn't see any cases with slowdown, but we saw varying speed ups across, and again with sort of varying differences in how much speed up we can obtain by pruning specific channels. So with cuDNN for ResNet layer 11, this was, I think, the maximum that we saw. So we saw 3.3x speed up by pruning somewhere between these 63 and 127 channels. And one thing to point out here again is that, sorry, I'll jump back here. We're not looking at accuracy specifically in this work. We're only looking at the inference time, but in general, the more channels that you have, so the further right you are along the staircase, the more accurate you'll be. So jumping back here, this is VGG. Again, we saw a 2.8x speed up roughly with channel pruning somewhere between 63 and 127 layers, or channels, sorry, channels. And then cuDNN on AlexNet, we saw about a 1.4x improvement. And we saw sort of improvements much earlier on here just because every network, every layer of every network is different in terms of the sizes and the filters that it's applying. So obviously here we started seeing improvements just after pruning maybe 2 or 3 channels here. So with the ARM compute library, let's first look at the direct convolution method. Sorry, just to go back quickly here. With cuDNN, we don't have as much observability. We don't have as much control over which method we use. So cuDNN automatically selects whichever algorithm it finds it thinks will be better, either if it's direct or IM2call or some other type of convolution. So we don't have much control over it there. But with ARM compute library, we can separate the direct and the IM2call operations. So looking at the performance of the ARM compute library with direct, we can see that as the number of channels increases, we have three different performance trends. And if you've got if you're in this sort of 500 channel range and you decide that you want to prune 1 or 2 channels, you can end up on any of these curves here, and there's a significant difference between the inference time of the top line here and the bottom one here. You can have 1.9x different. So you want to be really, really careful with how you're pruning these channels. So some of the speedups that we saw, for example, for ResNet layer 11, and we saw 16.9x speedup with pruning somewhere between 63 and 127 channels. For VGG, we saw similar speedup, so 14.7x was the largest that we saw. And then the other algorithm we looked at was GEM, which is basically the resulting operation once we do this IM2call transformation. And again, we saw sort of a couple of different performance trends. So here is basically looking at the lower end of this graph, and we can see that there are 2 separate performance trends. One's going above this top line and one above this bottom line. And the improvements that we saw by sort of pruning specific channels relative, again, to not pruning any channels is 5.2x for ResNet layer 11. We saw a 14.7x maximum speed up for VGG layer 7. And here we saw 2.5x for AlexNet layer 3. But again, if you look at the columns here, then there's varying differences in improvement that you can get throughout the layers and depending on the number of channels that you prune. TVM, which is it's another library, it's a self-optimizing library. basically that we can execute it on the ARM platforms, you can see that it's sort of a hybrid of the two previous libraries that we've seen. So the majority of cases fall on this optimal curve, but there are still multiple performance trends here, and you can, in certain cases, you can get more than 10x improvement by sort of choosing the right channel, the right number of channels to prune versus the wrong one. So you might end up all the way here instead of down here where you'd want to be. So the best performance, the best improvement that we saw with channel pruning for TVM was resonant layer 0 and 13.9x improvement there. So looking at this figure again, we want to explore some of the reasons behind the performance variation across the number of channels. So we looked at the ARM compute library through a GPU simulator. And if you're interested in the GPU simulator that we used, please have a look at this IISWC'19 publication. So we executed these workloads again inside the simulator, and let's focus on the differences between 92, 93, 96, and 97 channels. So you can see that 92 and 97 are on this slower curve. 93 and 96 are on the faster curve. So looking at the details for 92, we can see the number of arithmetic instructions, number of memory instructions. But what's surprising here is that we see two separate gem operations. Once we go down to 93 channels, which is on this faster curve, we only see one gem operation. And even though we've got more arithmetic and more memory instructions in this one gem kernel than in these two combined up here, the amount of overhead that you get with dispatching multiple kernels far outweighs the additional instructions that you have to execute in the GPU. So there's additional communication between the CPU and GPU. There's additional memory that needs to be set up. Additional jobs being dispatched. So that overhead is much larger than just executing a whole of extra instructions. When we go to 96 channels here, it's basically on the same trend line as 93. They're in that same sort of cluster of 4 that we see throughout this graph. We can see that we still only have one gem operation, one gem kernel executing here. And in fact, it's executing with the same number of arithmetic and memory instructions across these two configurations, across these two different number of channels that we're executing. There's a small difference in the number in the number of instructions for im to call, but that's negligible compared to the number of instructions that you're executing anyway in the gem kernel. So what we can see here is basically that for a specific cluster that you're looking at, if you're executing with 93 channels, you might as well bump that up to 96 channels because you can get that sort of improvement in accuracy without any penalty on your inference time. And when we jump back up to 97 channels, we again see this extra gem kernel being executed. So again, interestingly, the number of instructions for the first gem kernel are the same as for 96 and 93 output channels here. But again, we've got this sort of additional gem kernel here. And this is sort of a brief overview of the overhead and the CPU-GPU communication that we saw. There's a lot more control register reads and writes. There's initial jobs being dispatched here. And you can see this corresponds fairly well with the number of channels, with the runtime for the number of channels that we're seeing. So we also looked at the direct convolution method with the GPU simulator, and now across the number of channels, we didn't see any difference in the number of kernels being dispatched. So that was the same essentially for all the different channels, for all the different numbers of channels. But the interesting thing that we saw, the main difference that we saw, is the workgroup sizes selected for these different channels. So if we look at the two slower ones, 91 and 93 channels, 198 seconds, 202 seconds inference time, they both have the same workgroup dimensions, so 118, 118 here. And we know from previous literature and our own experiments that workgroup size has a major impact on the performance of a GPU. With different workgroup sizes, you might have different scheduling, you might have different caching between the different workgroups. So it's definitely something that you'd want to get right. It's definitely something that you'd want to exploit to the best of your ability. And the ARM compute library is open source, so we looked into the code. We looked at the heuristics that they use for selecting the optimal workgroup size. And it's based on this sort of approximation of how many mega operations we'll see, and also the size of the kernel. So basically, there's a bunch of different cases here. I think there's about 30 different cases. But the problem here is that this is all sort of a static analysis at dispatch time. There's no runtime information coming back from the GPU to aid this selection. So in fact, this number of mega operations, this estimate is very sensitive to changes in the compiler. For example, if you have, let's say, an add and a multiplication operation in one version of the compiler, by the next version of the compiler, that might be fused into a single operation. And since the release of the Bifrost architecture, there have been 20 different versions of the ARM compiler that have been released. So you could have huge differences between successive versions of the compiler, and especially across wide ranges of the compiler. And then the other thing is here that it really doesn't take into account the specific GPU that it's running on. So the Bifrost architecture, it's used in the G71, G72, G76, G51, and those devices vary between each other with the number of cores, the number of arithmetic units available in each core, the amount of memory that they use. So again, if you're selecting a workgroup, you want to optimize that for the specific GPU that you're using in that case, and not just a general approximation for the architecture. So thanks again for listening. Just to conclude, what we saw is that compression solutions can end up hurting performance. We saw a 2x slowdown for channel pruning. We saw that deep learning inference libraries perform their own optimizations. So cuDNN, ARMCL, and TVM all behave differently. They all have their own internal optimizations, some better, some worse. And the main takeaway is that selecting the right level of pruning should really be performed with the target device performance observations. So you really want to keep your target hardware in mind when you're optimizing these libraries. And we can see big speed ups, so 3x for cuDNN and 10x for ARMCL and TVM. And just to point out, our future work, current work is considering combined metrics for performance and accuracy, whereas this work just focused on the performance itself. So that's under submission to SysML, so keep an eye out for that. Thanks again for listening. Apologies again for not being able to be there in person, but if you have any questions, please get in touch. Thanks.